Let's do a quick review of the first 4 modules in College Physics 2, which are covered in Giancoli chapters 16 through 19. So the main concepts in chapter 16, which was on electricity and electric charge, are first of all you need to know all the properties of electric charge and be able to write them down and explain them. So you need to know that electric charge is conserved. You can move charge from one place to another, but you can't create or destroy charge. Electric charge is quantized, which means it only occurs in increments of the charge on the electron, which is 1.6 times 10 to the minus 19 coulombs. So you can add a charge of 1 electron or 2 electrons, but not 1.5 electrons. You should also know that charges can be positive and negative. There's 2 types of charge. You should understand the processes of charging by induction and by conduction, so you should be able to explain what they are, or if you're asked a question where you're given a series of steps in a charging cycle, you should be able to say whether the object is positive, negative, or neutral at the end. You should understand Coulomb's law, which is the force between 2 charges. You should know it's directly proportional to the charges and inversely proportional to the square of the distance between them. So you should be able to answer questions about the direction of the force, which is attractive if the charges have opposite signs and repulsive if they have the same sign. You should be able to do questions where you're asked what's the direction of the net force on a series of charges. And you should be able to compare forces. So what happens if you double Q, or what happens if you double R, for example. You should be able to answer questions about the direction of the electric field similarly, what the net electric field would be from a group of charges, and again compare the electric field if you change the charge or if you change the distance away from the charge. Remember, the electric field is kq over r squared. There's only one charge involved. You're sitting at a point, a distance away from that charge. You should be able to relate the electric field to the electric force. Remember, the electric force is equal to the charge times the electric field. So the field and the force are in the same direction if the charge is positive, and they're in opposite directions if the charge is negative. You need to be able to understand the properties of electric field lines. You should know that they never cross each other. The direction of the electric field at a given point is tangent to the field lines. You should know electric fields come out of a positive charge and into a negative charge. And you should also be able to draw the electric field lines for a given charge configuration. Or if you're given a drawing, you should be able to interpret what's going on. So which charges are positive and negative, which are bigger and smaller. And all of these different types of questions showed up in the actual lectures, so you can go back through the lectures, and now that the due date is passed, there's a review version where after you've answered the questions, you can go back and review the questions, and there's an explanation explaining the answer to all the concept questions that were in the lecture. So what kind of calculations will you see? Well, absolutely positively I can tell you that the long answer question, the one that's worth the majority of the points in this chapter, is going to be a calculation of either the net field or the net force at some point due to a collection of point charges. So we did problems on both of these in class, and there's lots of problems that I have up online. Make sure that you can do these problems. So you're going to have to be able to do vector sums. So you're going to have to calculate the field or the force from each charge at that point. You need to figure out the direction. You need to break them down into components, add them together, and then be able to get the total magnitude of the net field or the net force and the direction. When you do the problems on the test, make sure you read the problem carefully. Some of the tests will ask for field, sometimes it'll ask for force. And make sure you solve for the right one or you won't get the correct answer. Short calculations, there will be at least one very short calculation, which could be something like relating the charge to the number of electrons. So again, you had a problem like this on the homework, where you move a certain amount of charge and ask how many electrons is it, or maybe you move a certain number of electrons and ask how much charge then is moved. You should be able to calculate the field or the force at a point due to a single charge. And you should be able to calculate the electric field given the charge and the force, or vice versa. So again, remember that force is equal to charge times electric field. How about chapter 17? So the first concept, you need to understand how to get the sign, so whether it's positive or negative, and also the size of the work done, the change in potential energy and the change in potential, when you move a positive charge or a negative charge in an electric field. So again, go back to the online lecture and review what we said for if you move a positive charge in the direction of the electric field or against the electric field, what's the work done? Is it positive or negative? What's the change in potential energy? And what's the change in potential? Remember that the easiest way to do this is to calculate whether or not the object's going in the direction it wants to go or not. If it goes in the direction that it wants to go, then it's like dropping a ball. Then the thing speeds up, and so then the work is positive, and then the change in potential energy is the opposite of the work, so then it will be negative. The change in potential is equal to the change in potential energy divided by the charge. So it could be either positive or negative depending on whether you have a positive or negative charge that's moving. If the thing is moved in the opposite direction to what it wants to go, then it's like throwing a ball up in the air. It's going to slow down, so the work is negative. The change in potential energy will be positive, and again, the change in potential will be either positive or negative depending on whether you're moving a positive or negative charge. And when you do these problems, again, remember the positive charge wants to go in the direction of the electric field, and the negative charge wants to go in the direction opposite to the electric field. So again, go back and review this. Make sure you can do problems like this. What happens if you move the charge perpendicular to the electric field? Well, that's like moving a mass horizontally. You don't store or release any potential energy as long as you keep it at the same height. So there's no change in potential energy and there's no work done if you move an object perpendicular to the electric field. You should understand how the potential varies for a point charge. So the potential V is kq over r. So again, like we said for field and force, you should know what happens if you change the size of the charge, and what happens if you change the distance you are away from the charge. Potential is not a vector, it's a scalar, so it's going to be either a positive number if it's a positive charge or a negative number if it's a negative charge. You need to understand the properties of equipotential surfaces, and again you need to be able to either draw the equipotentials or to interpret a drawing of equipotentials. The next section of this chapter was on capacitors, so you need to understand capacitors. So for capacitors, for parallel plate capacitors, the capacitance is directly proportional to the plate area and inversely proportional to the distance. So again, you need to be able to do problems where you're asked what happens to the capacitance if you increase A or decrease A or increase D or decrease D. And the charge that's stored is directly proportional to the capacitance. So I might ask you what happens to the amount of charge stored if you increase the area or increase the distance, for example. So you need to be able to do problems like that. You need to be able to relate the charge, capacitance, and voltage for a capacitor. So if I increase Q, what does that mean about the voltage? If I increase V, what does that mean about the charge that's stored, for example? And again, you need to explain what happens when you put a dielectric in the capacitor. So when you put a dielectric in the capacitor, there's an electric field that's set up in the dielectric that opposes the main electric field from the charges on the two plates, and that decreases the voltage between the plates, and that increases the capacitance, and it increases how much charge is stored at a given voltage. So again, go back and review all the concept questions within the learning module online and make sure that you can do them and understand the answers. How about calculations? Well, for this chapter, there's probably going to be a couple of sort of intermediate length problems. You need to be able to calculate the total voltage due to a collection of point charges. You need to be able to calculate the work required to assemble a collection of point charges. And again, make sure that you can do these two types of problems. I've got examples online. We did examples like this in class. So go over all the sample problems. Make sure you can do it because you're going to see one or the other on your test. For a capacitor, if I give you the dimensions of the capacitor, you should be able to calculate the capacitance, the charge, the potential energy that's stored with and without a dielectric. And again, this is similar to the question that we did in class. Short calculation, I might give you a very simple calculation of what's the voltage at a certain distance away from a charge, or how much work is required to move a charge a certain distance in a field, for example. Or I might ask you to calculate the electric field given the voltage and distance and vice versa. Remember, electric field is equal to delta V over D. All right, Chapter 18. What are the main concepts? This was a really quick chapter. You need to be able to write down Ohm's law. You need to be able to explain ohmic and non-ohmic materials, what they are. You need to be able to draw the IV curves for an ohmic material and a non-ohmic material. So you need to understand those graphs, and you need to be able to know how to get the resistance from a IV curve. You need to understand how the resistance of a wire depends on the length of the wire, the area of the wire, and its resistivity. Remember, the resistance is directly proportional to the length. If you make the wire twice as long, its resistance is twice as high, and inversely proportional to the area. The resistivity is a constant that depends on the material. All right, so the resistivity depends on what the material is, whether it's copper or iron. It depends on how pure the material is. The higher the purity, the lower the resistivity, and it also depends on the temperature. The higher the temperature, the higher the resistivity. Remember, resistance is just like friction. It's the resistance to the flow of charges. So you can imagine that as you increase the temperature or you increase the amount of impurities you have in the material, there's going to be more scattering of the electrons as they pass through the material. So you need to be able to compare wires, and if I give you two wires of different lengths or different areas or both, you should be able to compare the resistances of the wires. You need to understand the concept of electrical power, how it increases with current and with voltage. And you need to be able to explain the difference between AC, alternating current, and DC, direct current power, and know how to calculate the RMS values for AC. What kind of calculations are there? Well, the longest kind of question I could give you would be one where you calculate the resistance of a material given its dimensions. And short calculations could be something where you're doing an Ohm's law calculation with either calculate I given V and R, or R given V and I, for example. Calculate the power used in something. For alternating current, calculate the RMS values or the peak values if you're given one or the other. And again, go back and look at the questions that we did on the group problems in class. You should be able to do those calculations, and if you can do them, you should be good for the test. All right, the final chapter is a really long chapter, so you need to understand for resistors and for capacitors in series and parallel what's the same and what's different. So for resistors that are hooked up in series, the same current flows through the resistors, but the voltage across them is different. If the resistors are hooked up in parallel, then the current splits up, so the current is different, but the voltage is the same. For capacitors, when capacitors are hooked up in series, the charge is the same, but the voltage is different. And so you'll notice for capacitors and resistors in series, for both of them, it's the thing that's to do with charge that's the same for each of them. For capacitors in parallel, it's the voltage that's the same and the charge is different. So for capacitors and resistors in parallel, the voltage is the same for both of them. You need to be able to interpret circuit diagrams to figure out which elements are in series and which ones are in parallel. So remember, if things are in series, then there's no junction between them. There's no way that current or charge can move in another direction. All the charge has got to flow through both of the elements if they're in series. If the things are in parallel, then you have to have just a wire connecting one end of the elements and just a wire connecting the other end of the elements. If there's anything else between, like a junction or another resistor or a battery or a capacitor, then they're not in parallel. You need to be able to write down Kirchhoff's current law and Kirchhoff's voltage law. So Kirchhoff's current law tells you that the sum of the current into a junction is equal to the sum of the current out of the junction. And Kirchhoff's voltage law says that if you add all the potential changes around a closed loop in a circuit, it should add up to 0. And you need to know the different rules, of course, for when you pass through a battery from positive to negative or a resistor in the direction of the current or against the direction of the current, whether the sign of the voltage change is positive or negative. So you need to review that. Then you should be able to use the Kirchhoff's current law and Kirchhoff's voltage law to write the equations for a junction or for a loop. So if I give you a sample circuit and I ask you to write down Kirchhoff's voltage law around the outside of the circuit or around the left-hand loop or the right-hand loop, you should be able to do that. The last topic in the chapter was RC circuits. So in RC circuits, you hook up a resistor and a capacitor to a battery, and you should know how the current, the voltage, and the charge vary as a function of time for that after you close the switch. And then also you should know how they vary for discharging circuits, where you get rid of the battery, the capacitor is charged, and you hook it up. So you should know the dependence of those, and you should be able to draw them. So if I ask you to sketch the voltage as a function of time for a discharging circuit, or the charge as a function of time for a charging circuit, you should be able to draw me a sketch of what's going on. You should also understand the time constant. All right, what kind of calculations will there be? Well, there's a whole bunch of different topics in this chapter, and so you'll probably see a number of sort of intermediate length problems. So I might ask you to calculate the equivalent or total resistance or total capacitance for some circuits. And obviously it's not going to be a circuit with 10 resistors or 10 capacitors in it, since that would take too long, but you need to be able to do a circuit for 3 or 4 resistors or capacitors relatively quickly. You should be able to calculate the current or charge for capacitor and the voltage on a given circuit component, again for a simple circuit. And you should be able to calculate the time constant, current, charge, and voltage at a given time in an RC circuit. So if I tell you what the R and C are, what voltage you hook the thing up to, you should be able to tell me after a certain time what's the current, what's the charge on the capacitor, what's the voltage on the capacitor, for example. There won't be time for me to give you a long Kirchhoff's law problem, but you should be able to do like what I stated in the concept section. You should be able to write down the equations for the loop, but I won't expect you to do a Kirchhoff's law problem on itself, since that might take 20 or 30 minutes. So in summary, you should have seen that the long answer questions that are going to come up on the test and the concept questions are very similar to things you should have seen already. So the long answer questions are similar to group problems that we did in class, and also very similar to questions that are posted as sample long answer questions for you to do. And the concept questions are similar to things that appear in the lectures.